Hello everyone. Today we have Anurag Upadhyay from Dunn Associates. He's a PhD candidate at Utah, and today he'll be talking about Python visualizations and OpenSeesPy visualizations command for post-processing. Anurag developed get rendering post-processing commands for OpenSees Python version. So it would be good to know today. So thank you, Anurag, and it's all yours now.
Thank you, Pawan. Everyone can hear me, I guess?
Yep, at least.
Okay. Hello, Dr. Scott.
Hello, we can hear you. Yeah, good to see you.
Okay.
Yeah.
So this is not some OpenSees technical presentation. It's more about how you can use these visualization commands to make your model better and kind of debug your model. So let's go towards the OpenSeesPy visualization commands first, and just to see the commands in there and what you can do. So these commands can be used for OpenSeesPy and OpenSees Tcl both. How it works is there is plot model and plot mode shape commands. They can get data directly from OpenSeesPy model. But if you want to use it with OpenSees Tcl models, you have to create an output database first, which is really easy. So this create output database command, it's or create ODB. This is to be used with OpenSeesPy models. In order to use with OpenSees Tcl, if you go to point 9, so all this information is there on OpenSeesPy website. If you go to post-processing module and get rendering commands and plotting OpenSees Tcl output, and you have to download this file here, get rendering.tcl, and call it in your OpenSees Tcl model. And then, okay, let's look at the script of this get rendering command. Okay, this is get rendering.tcl. This is the file you will call in your OpenSees Tcl model. It just creates a procedure here, create ODB, which has the same name as you would use for OpenSeesPy command. And 3 inputs are there: model name, load case name, and number of modes to be recorded. In this file, there are 2 examples here. So if you want to record 3 mode shapes and no load case data, then you have to write this command, create ODB, and then model name, which is, let's say, two-span bridge, and then load case name none. So when you put none, it doesn't record any load case data in there. And then 3 is the number of modes you want to visualize, and it will record data for 3 number of modes. This same command can be used multiple times in the same model. If you want to create database for different load cases, let's say pushover or dynamic or something else, then you can just same model name, two-span bridge, and then let's say pushover, and then next time you don't have to record the same mode data again. You can just write 0, and then it will keep these 3 mode shapes in the output database folder. Okay. So, and the same information is here. There is a little basic script here, how to call this procedure in your OpenSees Tcl model. So you source get rendering.tcl, and then after you define your entire model, you write this command, create ODB, and then model name, load case name, and number of modes you want to record. And then you don't have to know Python in order to use these visualization commands. They're really easy. You just have to write the command, and then it will do things for you. Okay, so let's go back to the presentation and see how I used it in my research. Oops. Okay, so this was the first part of my PhD research. It was seismic analysis and performance-based seismic retrofit of an old bridge bent here. Utah had this old I-15 corridor, and there were a lot of old bridges, which the UDOT finally demolished and then constructed new bridges all over. But then there was this little study we did if we wanted to retrofit them. So this is the bend, one of the bends our research group tested physically, full-scale bend. Okay, so it has piles, 3 columns, all on piles. So 4 piles on the extreme ends, and then 5 piles in the middle, and concrete columns, concrete bent cap, and then steel girders on top of that. And here the cross section of column and the cap beam. So our aim is to model a 4-span 3D curved bridge now. And it's a really complex model with nonlinear soil springs and nonlinear columns, deck, multiple joints in deck, and then pounding at the abutments and then abutment soil. So a good way to do this or to achieve this modeling is to break down your model into multiple pieces and then start with the smallest and the most important piece you want to model. So the most important piece for me was this one single column bend, this one. This is the most important thing for me because this is what we tested in situ, and then I was supposed to match OpenSees model to recreate that pushover analysis. So these were the steps I took in order to create this huge model. So first I created a 3-column band with elastic sections and then converted them to nonlinear sections and checked if they were working or not. And then I modeled a pile cap, single pile cap separately and see if that works or not. And then again, I combined that pile cap script with the single band script and then tested that. And then finally I achieved that 3D 4-span bridge. So using the same OpenSeesPy visualization command, so just plot model and then model name, it will show you what you have created or what in your OpenSees model. These are the element numbers here, 45, 47. So you can see if you have connected them well or not. This is for the visualization of general connectivity. You might still get non-convergence issue when you run gravity or modal analysis. But this is just for a general visualization if your elements are going in the right direction or not. So first create this entire thing with elastic sections. And you can use elastic section with nonlinear beam column elements, which is a really great thing. You can quickly switch from elastic section to nonlinear section and then see if you get the same periods. So run gravity analysis. If it works, it's good. If it does not, then there is some connectivity problem. And then check mode shapes. So since this is one single band in a 3D space, it makes sense that first mode is out of plane. If it's twisting or doing something else, then there's something wrong with the model. It's really important to make sense of the mode shapes. That's how you achieve a really good model and you can trust your dynamic analysis. If your mode shapes are wrong, you cannot trust the results from your nonlinear dynamic analysis. They will not make sense. Okay, so again, so there's a simple command in OpenSeesPy get rendering library is just plot mode shape, and then you put your output database folder name and then mode number, and then it will plot for you. So mode 1, mode 2, mode 3 is the lateral one. So if you were to do a lateral nonlinear dynamic analysis on this band, you should consider mode 3, and then you should scale off all of your ground motions for mode 3, because mode 3 is the lateral one, not mode 1. And that's hard to understand if you cannot visualize your mode shapes. Okay, so now from elastic sections, switch to nonlinear fiber sections. Again, because you're still using nonlinear beam column elements or force-based beam column elements, your results should not change. If, however, your results change in terms of mode shapes, there is some problem in creating that fiber section. So check that definition. So mode shapes for both of these cases should be the same. Okay, so let's go ahead with single pile group. Since this pile, each pile has 60 elements and then almost 60 soil springs, and I have 5 piles in the center pile cap and then 4 piles in extreme pile caps. It gets complicated, creating all the nodes and element connectivity and assigning PY springs. So it's better to just start with one single pile cap and see if the gravity analysis makes sense or mode shapes make sense for that. So I just created this center pile cap here, which has 5 piles, and then pile cap is just modeled as one node here, and all the mass is lumped there. So I did gravity analysis, that went fine, and then I checked mode shapes. Again, checking mode shapes or mode shapes of a single pile group doesn't make sense, but it gives you a sense of connectivity or how successful your modeling is. It's pile cap or pile group is just like a tall building, that's all, with multiple springs all around. So the mode shapes should make sense in that case. So, so mode 1, mode 2, again, these numbers, they don't have any significance. It gives you an idea that your modeling is successful. You don't have any convergence issue while running mode shapes or eigenvalue analysis. Mode 3 is infinite. I'm not worried about that because it's probably trying to get the vertical mode out of it. And when you use that plot mode shape command, the window the Python generates is interactive. You can zoom in and zoom out, and you can check multiple angles with that. We'll go through that later. Okay, so now I connected the pile group script with the single bench script. And so I'm getting closer to what we tested in out in the field. So this is what we tested, a single band with 3 pile groups. Again, run gravity analysis and see if that runs successfully, and run mode shapes and see if they make sense. So if you remember, mode shapes for a single band without any pile caps or pile groups were, first mode was out of plane, and then second was twist, and third was lateral. You should get similar mode shapes again. Your period may change because of the soil structure interaction now, but adding these piles or pile groups, they should not change how your structure behaves. First mode should be out of plane because it's just a planar structure in 3-dimensional space. Second twist, and then third lateral. So I'm happy with that. Okay, so Now I'm one major step closer to the entire full bridge modeling. Now I have one script for band and pile caps with piles. I just changed the coordinates and everything to create this full band, and then I assigned elastic deck elements in that. So okay, so since this bridge band was old, it was like constructed in 1965. It did not have seismic detailing. It did not have any good confinement. So when we tested, we saw rebar buckling, vertical rebars. They were buckling. So I had to use something that could model that. So reinforcing steel material can model buckling internally, or you could use hysteretic material model, calculate when the rebar buckles based on the clear distance between the stirrups. Concrete 04, I had some colleagues using Concrete 02 in their modeling, but I went for Concrete 04 because it's an old band. It does not have, the concrete was already old. It did not have elastic stiffness in it. And the Concrete 04 crushes, and then it gives you a residual stress in the material model. And that was helpful in recreating that failure mode we saw in the test. Okay, so this is how Concrete 04 is. It just goes to 0 here once it crushes, and that's what we saw when we tested the bend. All the concrete chunks started to come out and there was no strength in that area. If you have a good confined concrete column, you will not have those chunks of core concrete come out of the column. So Concrete 04 may not be a good choice for that. Okay, so after everything, I had the model, and then I checked with gravity analysis. Gravity analysis was completed successfully. And then let's check the mode shapes again. Since it's a simply supported bridge, and there's always gap between deck and the abutment here. So the bridge or the deck is free to move in longitudinal direction. So it makes sense that first mode is kind of in longitudinal direction. Second mode here is lateral direction. That makes sense because that's how it should be. And third mode is kind of each individual bands were twisting. And if you see here, this deck here and here, there's a shift between these two decks, and it's because they are not connected. It's a simply supported bridge. So deck is segmental instead of a continuous deck. So I'm fine with that mode shape. Now the retrofit was to be, the retrofit technique we explored was a BRB retrofit. BRBs are buckling restraint braces. Like you see in conventional braces, when they go in compression, they buckle. But buckling restraint braces, they have this core, which is basically the brace, and then you confine it inside a steel tube and then fill it up with concrete with some kind of gap between the steel core and the concrete. So the steel core is still able to move and slide across the concrete because of that little gap. And it barely starts to buckle, but then it does not buckle. So you have to have enough gap between this core and the concrete so the core starts to buckle. You don't want it to buckle completely. You want to initiate that process so it can create these waves. If it does not have any gap between, or like if it's just composite steel and concrete, then it will have some other problems. It will try to buckle in global buckling which is like buckling of the entire brace instead of the core. And the benefit is that instead of this buckled behavior in compression, we get pretty symmetric hysteresis in BRBs. Okay, so let's talk about calibration here. So we did a lot of BRB testing at University of Utah. So one of the biggest BRB manufacturers, Core Brace, they are in Utah. So we test a lot of braces for them. So I used Steel 02 material model combined with pinching to recreate this BRB hysteresis. Steel 02 is symmetric, but in BRB we have additional strength in compression. And why? That's because of this phenomena here. When the core in BRB, it buckles, all these heads, they start to drag against this concrete, and it gains friction in compression. And that friction gives it additional strength in compression. So it's always not so symmetric. There's still additional strength in compression. And that's important to simulate. So I used pinching material model for that. Calibration was tedious. So my aim was to first match this force here, these points for each cycle. I was trying to match the force first. So, and since we know that it's not symmetric in compression, I'm not worried about that right now. First, I'm trying to match the force points in tension. Once that's matched, I have a symmetric behavior because of Steel 02. And then Steel 02 has parameters for strain hardening and compression and tension, and you have to play with that in order to get this strain hardening here. It's not exact match, but it's pretty good. Now let's see at the compression. We have this additional strength here, and it's about like 500 kilonewton, and that's a big strength for this BRB. So here, pinching material model plays an important role. How it does, like, you assign parameters in pinching material model only in this area. Other parameters in tension can be 0 or really close to 0 to avoid any numerical non-convergence issues. But I assigned a little higher stress in this area, so it could create that compression strength. Okay, so now that I have a model for band with all 3 pile caps, I tried to do pushover analysis and then checked if the results were matching with the testing we did. So this is how the bridge looked like. This was the part of old highway I-15, and then we tested a few old bands here, 3-column bands. One important thing here is, since we tested this piece of the highway, this deck is loading these 2 bands. So now this band is not seeing a full deck load on it. It's seeing only half deck load here. So I have to adjust that deck load in order to get this pushover curve here. It matches pretty well. I could see the buckling in rebar in compression and then core crushing after that. So we were happy with this result. And then I tried to see how the foundations are doing, the foundations we modeled in OpenSees versus what displacement we measured here during the test. And it does pretty well here. So this is the experimental curve, and then this is analytical. So our PY springs are working fine, our pile cap spring is working fine, and then overall the model is good to go for dynamic analysis. Before we do dynamic analysis, in in order to get the performance in terms of pushover, I cannot use the result from half deck load anymore because I'm modeling a full bridge, and then in that case, the bridge band will see a full load instead of half. So we can see the performance here. When I increase the load, it created additional stress at the bottom of the concrete, column concrete, and then we got crushing a little sooner than this half load performance. So I cannot compare the results of dynamic analysis with this half load pushover curve. I have to compare them with this full load. So, full load means higher P delta effects and then early failure, but little higher lateral force capacity. Okay, so we applied BRB in there. In order to quantify the results from dynamic analysis, we came up with these 3 or 4 different performance states. It's like, okay, the rebar yields here, and then we have cover cracking, and then cover spalling, and then the lateral capacity kind of goes down from there. And when we added BRB, our BRB yields here. So we have little extra energy dissipation in this area as compared to a band without any BRB. And then we have BRB buckling, fracture at this point, and that fracture was based on just the peak strain in BRB core. Okay, so, and then after that, all the cool stuff started to happen, nonlinear dynamic analysis. Everyone is happy to see that. Okay, so how I assigned BRB in this model was from work point to work point. Remember that, excuse me, our model looks like this. So I don't have any additional nodes here to connect BRB. There's a tutorial for simulating BRB on my website. It's pretty easy. You provide this work point length from here to here, and then ratio of core length to work point length, and then it just adjusts everything accordingly. So my ratio of core length to work point length was 0.55, 55%. And then, okay, I didn't know I had this cool transition going on. Okay, so this is the result after BRB application. So without BRB, the bare band was achieving near collapse status for MC level ground motion. After BRB, we just crossed life safety. So that's a good result. Another example of using visualization commands is, again, the second bridge. The second part of Ph.D. is this post-tension precast bridge. And so I had this model, it was working fine. I got first mode because these bearings here, they were fixed. So I did not have any longitudinal deformation or displacement in this bridge. This was just while I was checking the model, if the model was fine or not. So, and then since I had constrained these nodes here, I was expecting the first mode to be lateral, and which is fine. But then when I looked at the second mode, it had this strange movement here at the band, which I don't expect that, because in OpenSees model, this band it had 3 bearings here. 1, 2, and 3. And then only 1 bearing was going out of plane, kind of. And that did not make sense. So I went back and then checked the model, and then I realized that I had assigned a wrong property because I had so many springs in this, or link elements in this model. I missed one and then I assigned a wrong property. I fixed that. Now the second mode looks good and I can go ahead with pushover or nonlinear dynamic analysis. Another example is I was helping a student and that student sent me a file saying that it modes are infinite, like first and second modes are just infinite. And that did not make sense. And I checked the model. Okay, well, I checked the model. Let me show you the model. We can do some hands-on thing here. Okay. So this is the model here. And when I checked the model, that student had put a lot of rigid diaphragms in here to make it easy or to make the model work. But when you get rid of these rigid diaphragms, you can see that okay, just hold on. These nodes here for BRB, this is a three-story steel building with BRBs in it. This node here at the top of these two BRBs, it's not connected to this beam. And it's easy to make that mistake because in other software platforms, we don't have to create each node separately. Sometimes you just assign BRB and then it takes care of that internally. But this node here, 999, it was not connected to this beam anywhere. And then the program, the OpenSees script or program had singularity and it did not converge. There were no mode shapes. And once you fix that, mode 3 here, this mode 3 became the first mode, and then first two infinite modes were gone. So this is how you can use OpenSeesPy visualization modules. Let's do a little hands-on here to see how we use it. Still, a lot of people use OpenSees Tcl, because it's popular. It's all the people or experienced students, they have used Tcl. So, and if you use OpenSeesPy, you don't get much help. Okay, so this is one script. In the beginning, you call this getRendering.tcl here, and it calls out that procedure. And once you're done modeling everything, at the end, okay, that's a big model. Okay, so you call that procedure create ODB, which is create output database, and then name of the model you want to use. So let's say 3D building. Gravity is the load case name. So it will try to save all that load case data, deformed shape of the structure after this load. And then it will try to save first 6 modes and their shapes. When you run the analysis, it creates this folder here, 3D building underscore ODB, which is output database. You go inside, there are element information, there is node information. You can click on that. You can use all these data. If you know enough Python, you want to create your own things, you can use that. Here's all the mode shape data. For each mode shape, there's a, see, it's all first mode shape is always 0 because of that disconnect in the nodes. And then it saves model periods, which is again, it's showing infinite for now. Okay, And how I do visualization is I just create a Python script here. I don't generally use um, Spider or notebooks. I just use my own script here and then run them on shell, Python shell, or Miniconda or Anaconda. And to visualize, you just have to write this command here. First, you import that visualization module from OpenSeesPy. And after that, plot model command is right here. If we go to plot model command, it's here, and then it has a few examples here, what you can do with that. So if you are using OpenSeesPy for your modeling, you don't have to write this model name here. If you write plot model, it will show you your model. If you write plot model and nodes inside it, it will show you node numbers, element for element numbers, and then you can even see both. We will use this command here because we are trying to combine OpenSeesPy and OpenSees Tcl. So we have to write this model name, and then it will search all the data inside this name of this folder. Okay, so here's the plot model command. I want to see node number, element numbers, and then this is the model name, which is 3D building. So if I run that, okay, so this is how it looks like. You can quickly visualize your model. You can rotate them if you want to. You can interact with this window for deformed shape, for your mode shapes, or for model, and that's quite handy. There are plot model or display model command for OpenSees Tcl, but then you cannot interact with them. Once you click on the window, it freezes. So Python is pretty good at that, handling that interaction. Okay, so that's everything for visualization. I'm sorry, I did not have a huge presentation. I'm still in my office. If you have any questions, let me know.
Cool. Thank you, Anurag. Yeah. If you have any questions, please go ahead, guys. No questions from anyone? Okay, then I'll go ahead and ask one. So, Anurag, one quick question is like you have all these commands, right? So,
yes.
So, for example, if I want to customize my access and my other stuff using these post-processing commands, like for example, I want to change my access widths and all that stuff, more customizable. How do we do that? With this?
So this code is available on GitHub. It's here if you go to OpenSeesPy, and then inside pip dictionary, OpenSeesPy post-processing, and this getRendering.py. You can create your own local version of this. You can change things however you want. As of now, it does not have that functionality.
Okay.
I will add more functionality later. It just earlier Christian from British Columbia, he was helping me out, but now he has got a job, so he got busy. So maybe I need other students to expand this library here and make more functionalities. I'm going to add a few more functions soon. One of them will be live rendering. You can see what you're modeling live, and then it will have support for if you want to create nodes and elements using for loop or while loop. It will just show you everything in live, and then you can zoom into one little corner if you are trying to create, let's say, plastic hinge elements in columns and beams, you can zoom into that little corner and then see if you're assigning that element correctly or not.
Cool. Any other questions from anyone? No questions? Interesting.
This is Sylvia. Hi. I just have a
Hi,
comment.
Dr. Mazin.
Hi. I didn't know that this is really nice. I'm caught by surprise because I like how you've integrated it with the Tcl version of things. I don't have any questions,
you.
but I'm excited to start playing with it and see what
Okay.
comes from that. So thank you for doing this. This is really cool.
Thank you.
Yeah.
Okay, no questions. Okay, then I'll ask you one more, Anurag.
Okay, yeah, sure.
So in your 4-strand model, concrete model, can I ask a question about that model?
Yeah, sure.
So you calibrated your model using a pushover test and
Yes.
BRPs and everything, right? And then you
Yes.
did like a nonlinear analysis of that.
Yeah.
So pretty much you calibrated your model for static analysis and then you did a nonlinear analysis over that.
Yes. So the reason was because we tested this band here in field. We did not have any dynamic testing for that. So
did you do any free vibration or like snapback, something like that, because there is mass over it and everything, right? So
no, we did not do anything like that. So I should have put that picture here. So this is really tall band, just like a real highway band here.
Yeah.
And our team created a huge actuator right next to it. We constructed a huge actuator and we kind of pushed that thing, out there right next to the highway. So we did not have any free vibration thing in there.
Okay. Or like ambient vibration or anything, just in case, like, to see the periods are matching or not, because
so yeah, I know they do that.
Yeah, I do
but,
that. That's why I'm asking you.
Okay.
I do similar stuff. So that's why I was curious, like, how confident are you because I'm also trying to going to do some static to nonlinear stuff. So just sort of asking you, how confident are you to extrapolate that stuff there, or anyone else can comment too?
So the thing was that UDOT was already demolishing the highway, and my professor got permission to test a few bands, and they said that okay, we will demolish rest of the highway. We will leave these 4 bands for you to test, and then you can do whatever you want with them. Now it doesn't make sense to do vibration analysis because it's not that bridge anymore.
Yeah.
So the best way was to do this pushover test. And doing cyclic on this huge structure, it's really difficult and really expensive.
Okay.
I have another question since
Okay.
we're talking about the testing. You were talking about how to model the brace, you used steel O2 with pinching. What does that mean?
Okay, yes.
Did you do it in parallel or?
They were, yes, they are in parallel. Okay, let me pull up that script here.
So this is like pinching 4?
This is pinching 4, yes.
Yeah. So
I should have written the full.
No, you mentioned it, you said it. So
Okay.
a quick question on that then is, and I know steel O2 is real pretty, but why not just use hysteretic since it doesn't have to be symmetric? Were there other characteristics that you were looking for?
Okay, yes. So I don't know why I didn't use hysteretic. Probably because I wanted hysteresis to look really curvy, like
Yeah,
this,
also,
instead
yeah,
of choppy line-wise.
yeah. Also,
Hysteretic material cannot have smooth curve. At max, we can just put 4 input points in there.
yeah. No, and also realize I don't think it has. Does it have kinematic hardening? The hysteretic? I'm not sure.
No, it does not.
Okay, and that's what you wanted in there too. Okay,
Yes.
and so the way you got the symmetry or the anti-symmetry is by doing it in parallel with pinching of 4.
Yes.
Okay. Another question. You said you use reinforcing steel.
Yes.
Have you been doing any work with it? I tried reinforcing steel a long time ago and I couldn't get it to converge and work well for me. You haven't had any problems?
It converged well with static pushover analysis and dynamic analysis for long period earthquakes. But if it's a pulse type earthquake, it's really bad. It did not converge well in that.
Okay. So just sometimes it worked. Okay.
Yes, and I also talked to the author about it, and he said that he's aware of this problem, but he doesn't have any solution for that.
Sylvia, I used reinforcing steel for cyclic, for large displacement cyclic loading. It works well. Convergence wise, I mean, I need to use a very strong solver, but like go through a lot of steps, but like it does converge and do a good job.
Even in a real structure, not just as a uniaxial material.
Yeah. So I was calibrating using the field test data again, my file tests and other stuff. It was doing a good job.
Good.
I mean, I
have
did recently, so like.
I might have to revisit it.
But
Anurag,
I didn't do that.
Anurag, you said you're in your
Yes.
office, and I'm very impressed by your office. It looks like you're at the beach. So
Yeah,
I'll.
my office pays me well for vacation. Thank you.
Very nice.
Ted Cruz with you?
Oh.
Any other questions from anyone else, guys? I mean, I have a lot of questions I can keep asking Anurag.
Yeah, sure.
So the other thing was like you use POI springs, right? I use them a lot too. And like, how did you calibrate those springs and like using CPT data or like what did you?
I used CPT data for that.
Okay, so is it like a clay or sand solid?
Okay.
Clay or sand there?
Okay. Should I open my script?
Yeah.
If you want that.
No, I was just curious, how did you, because there is no proper way to convert the CPT to POI springs, right? Like in theoretical equation. So how did you do that? Because that will help a lot of people, I think.
I used those basic equations from, I guess it was American Geo, wait, APA?
API, American
API, yes.
Yeah.
Yeah, I'm sorry, I did that like 2 years ago.
So you use the ones available in, directly available in OpenSees, like, so you didn't have to change any equations or any way you to.
No, I did not.
Because like I did find them for clay, they were not doing a good job. So like I had to, I mean, PY springs are doing fine, but like getting the P values, P ultimate and Y50 values, I had to do it based on the real time. I had to go and talk to consultants and get like what they're doing real time because the equations are not doing a good job. So maybe I'll do present sometime.
It depends on what you're trying to look for, the failure and everything. Focus of this, my research was not on soil.
Okay.
I modeled pile and pile groups just to match the data. And when I did my IDA stuff, I changed all these piles from this pile group to single soil spring at each, and that which would match the lateral displacement and force in pushover analysis. So
equivalent.
And that saved me a lot of time, because for dynamic analysis, having these many py strings, it's like it kills you.
Yeah, I'm doing that now, so this takes a long time.
So
But
yeah, it all depends on what your what focus of study is.
so I was just curious because I did face that issue like for a long time, so and it took a while to figure that out. So I was curious how you did that.
Okay. Yeah, sure. Discussions always help.
I have another question. We can go back
Okay.
and forth on with questions here.
Yeah,
sure.
sure.
Well, no, since you said you use the OpenSeesPy a lot, and you also said that you're calling it straight from, you're calling Python straight from your DOS or your command window.
Yes.
How do you, so could you do that? So what I'm trying to figure out is when I run a lot of analyses in Tcl, it's great because I can just create a batch file that just calls OpenSees with the input files, and I can run, and therefore I can run a lot in parallel.
Mm-hmm.
Can you do, could you do, how would you do that with OpenSeesPy? Would you have to call many instances of it, and is it possible?
Okay, so it does not automate that. If you were to run a lot of OpenSeesPy scripts at once, I would just go ahead and create multiple or start multiple these Anaconda prompts or
ID, yeah.
shells. Yeah.
Okay, so you have to, you can do
Yeah,
that.
you have to do manually.
Okay.
So multiple IDEs and run multiple models at once.
Yes.
That's what
And I have done like I've run six analyses at once on my computer.
You got a big computer.
And so you just have, you just start off instances of the shell and call
Yes.
up the program.
Yes.
Okay. So could you, so I wonder if you could put that calling up the shell into a batch file.
I don't know how that works on Windows. I know Linux can handle starting multiple instances, but Windows is tricky.
Oh, okay. So what you're doing it, what you're saying is you're doing it in the Linux. You're not doing it in Windows.
No, I use Windows. I have tried Linux, and I know there's a way I can run multiple Python files, and it's more flexible in that case. It can start multiple instances of Python at once.
But with Windows, you can too, though.
With Windows, I cannot. With Linux, I can.
Oh, okay. So you cannot run. So let me, I misunderstood.
Yeah, on Windows, from one, I cannot run in batch mode unless I create my own script of doing so.
Okay.
Yeah, I have not done that on Windows. I will show you what I did. It's just, really amateur.
But in Linux or in Windows? I'm a little confused as to where you did it.
So I use Windows for all my analysis. So what I do is like, okay, this is my script for running dynamic analysis for multiple earthquakes. What I do is like, okay, I just change here earthquake number from 1 to 10, and then I run this script, and then.
But this is Tcl. I mean,
okay,
from Python. Tcl's easy to run many instances. I'm not worried about it. I know how to do it in Tcl. What I want to know is in OpenSeesPy, can you run many OpenSees?
I can do the same thing with OpenSeesPy. You can run multiple this kind of windows.
Okay.
Okay.
Okay, so you can have multiple Anaconda prompts.
Yes.
Okay.
You can have multiple and then let them run on these multiple prompts.
Okay. That's okay. That's good to know, because that's what I was trying to figure out. And I'm like, there's got to be a way.
Yeah, I mean,
no, I'm not that expert, creating those parallel analysis on my Windows machine. It's
okay.
It was not worth the time. I can just do it in really easy way, so I just did that.
So you just go to your Linux machine to do it.
Yeah, Linux, I can do that.
Okay. All right, thank you.
I don't use Linux anymore because I started this Python and Linux thing when I had my old laptop, and that could not handle MATLAB. So before going to meet my professor, I had to start MATLAB 15 minutes ahead so I could show results to my professor. So I just switched to Python after that, and Linux. So that started my interest in Python and Linux.
Okay. All right, thank you.
So, Anurag, I have a question on, I think it was slide 12,
Okay.
where you showed the mode shapes for the piles.
Yes.
Like the piles are really deep, but only like the upper 10% is deforming with these mode shapes. So couldn't you just cut off the piles and put a boundary condition there and no difference, right? And you'd save a lot of computational expense.
So yeah, it's a common thing. I saw a lot of literature where it's a common thing that first 10%, 15% of the piles it deforms unless there is a liquefaction. So these piles they were not for liquefaction; they were more for the load bearing through skin friction and end bearing. So that's why we have such long piles here. So yeah, if I cut my pile group up to this point, or like just keep 15% pile length here, I should not change the results much, as long as I'm creating this boundary condition here really well.
So one thing we do, other thing we do to reduce the computation is increase the element size there at the bottom. Even though the depth is big, we just make it like 2-3 meters deep so that we have one spring there. So it also reduces.
Yes, that's a good way to, again, since for me using pile was just one-time thing, so I can see my pushover curve. So I did not dive into creating multiple different elements.
But I mean, if it's just there for vertical load, right? I mean, you can just
These piles are mainly
cut it off, put a
load.
pin, and not worry about it, right?
Yes.
Yeah.
So I just created multiple pile segments or pile elements of the same length, and that's why I had a lot of elements in there.
Okay. Thank you.
Okay.
Any other questions, guys? Any other questions from anyone?
So this is how I created pile segments. Like each pile has 60 segments in there, and then it's just elastic elements, because I don't think we'll see any kind of nonlinear behavior in piles, only the py springs or so yeah, I had two different kinds. So I used just two node link elements for those py springs here, and then it's pretty, a lot of elements in here. And the thing with curved bridge is the direction of these py springs, they change for each bend because the bridge is curved. So the direction of bearing elements, direction of pounding, direction of py springs, they all change based on the bend. So for this bend, longitudinal direction is here and then transverse is here, but for this bend it's a little tilted, so there's a little twist in here. So that was a tricky thing to model.
Cool. Any questions? Okay. Anyone? Any questions? Or everyone understood everything today?
It was not like really OpenSees technical thing. It was more visualization.
Yep.
And I'm sure it's helpful. I think
oh yeah, it is. Because I know a lot of people were like trying to use these. So, oh yeah.
Okay.
I have one more question. What are you using the two node link for?
For soil springs.
you use PY strings, right?
I used both. This model is with two node link elements. So I used both PY and two node link. Yeah. So let me see if I can find my PY springs here. So I created this uniaxial material with PY springs. That's the material model.
Yeah.
And then I assigned them two node link elements. So that's just
Why
an
the
element.
two node link elements instead of zero length elements? Or
Yes. So I never use zero length element. I always go for two node link element, because when the length is zero, it just converts to zero length element by default.
okay.
I mean, is there a reason for that? Like, is it faster, or is there a reason for using two node link?
Two node as compared to zero length, or
Yeah.
it just when I use zero length element, it just confuses me at multiple places.
Okay.
So when I use any kind of link element, I have a set concept in my mind how to visualize that, and its axis and everything. So it's just easy for me to use two node link element.
Okay.
Is there a difference, Dr. Mazzoni?
I haven't used the two node link element. I've had, it's funny because I come in from the other approach. I was going to use that, and then I didn't like I wasn't sure, maybe because I couldn't use certain materials with it. I can't remember exactly why, but I kind of went the other way, and I went back to using a zero length element and just accepting the warning. Oh, because you can't put it a
Zero length section? No.
yeah, so I was using sections, and I think I was using the coupled section or something like that, because it was pretty much for a demonstration of, and so I was like, oh, I can show the length, but then I couldn't do the coupled section.
Okay.
And so, because that allows you to do kind of like an axisymmetric response. So, and so let me ask you, I mean, I know it's a curved bridge, but the soil doesn't quite have directionality. So
it does not. That's true. So again, there is no clear way to handle that because it does not have any directionality. I just wanted it to be consistent with the direction of the band, or the lateral direction of the band. So when my band is moving in through its lateral direction, I don't want piles or springs to compress in some other direction, because then it will create a little twisting in the band.
So when you have pile groups, it actually affects the resistance, the stiffness of the spring, and there's some ratio depending on the geometry.
Mm-hmm.
And so in that case, the orientation of, your bent and your pile groups would come into place, I guess.
Yes.
So, okay. Interesting. Thank you.
Cool. I mean, one last call. Any questions? Anyone? If not, then we can conclude.
Very good.
Thank you.
Thank you.
Okay, then Anurag, I think like no one has any questions now. So I'll think like so thank you, Anurag, for presenting today. It was helpful, and I think like people who want to use your commands will definitely, need to look at it. It will be helpful. And next session, we have Christian from University of California, Fullerton, presenting. He'll be presenting on RC walls and some of the things he's been working on. So yeah, I'll send everyone like out an email soon. Cool. And thank you everyone for attending.